Hello, in this video we're going to take a closer look at power series, in particular how to determine when a power series converges. So we're going to be looking for the interval of convergence and the radius of that interval of convergence. First, just a refresher on what a power series is. This is our general formula. Okay? There is going to be an x value in here whenever you're dealing with a power series, and then some definition for that coefficient, which could be just about anything. So really we're looking for that x minus x naught to the k showing up to identify a power series. Now, when we spent 2 whole units talking about series and determining whether a series converges or diverges, and with those, because there was no x variable, it was always converges everywhere or diverges everywhere. So we didn't even talk about, maybe places where it might not converge. But when you introduce an x into the series, it changes everything. Now suddenly, if I plug in a particular x value, maybe the series doesn't converge there. And so this section is all about figuring out, well, what x values can I plug into the power series and get a convergent series, okay? Now there's really 3 scenarios that we will run into when finding the interval of convergence. It could converge for every x value. No matter what I plug in, I get a convergent series. It could converge nowhere, which I say almost there because it will always converge at your x naught value. Whatever that x naught is for the power series, it will converge there no matter what. But maybe it doesn't converge anywhere else. No other x values will work. So that's what this first one looks like. If it only converges at x naught, then that little dot right there, that is my interval of convergence. And then everywhere else, every other x value, the series diverges. In that case, my interval of convergence is just the point, x equals x naught. And because the interval is just a single point, the radius of that interval, or half of its length, is going to be 0. If the series converges everywhere, well, anywhere on the number line, any x value I plug in will give me a convergent series, which means that the interval of convergence is negative infinity to infinity. And that radius, so half of the length of an infinite interval, would be infinity. Now the third option, these are to the 2 extremes. The third option is somewhere in between. So that would look something like this, where I end up with an interval that goes from one number to another. It's a finite set, and it's more than just a single point. And the radius of convergence, again, would be half of the length of that interval. So the distance from the center, which the interval of convergence will always be centered around your x naught value, out to one of the endpoints. That distance will be the radius of convergence. Now, something to note with this third case, these are the longest ones, very long problems, so you're going to want to strap in when you do one of these, and we will do an example of this together. But what I don't get initially is whether the endpoints are convergent or not. So we're always going to have to test the endpoints separately to determine whether the series converges at those endpoints. So something to keep in mind as we do this. We're always going to have to test that separately, which is an easy thing to get to do on these. Okay, so let's do an example. So I want to find the radius and interval of convergence for this power series. And I can see that it's a power series because I have an x to the n here. And pretty much you're going to have 2 choices. We have a ton of convergence tests at our disposal, but really it's always going to be either the ratio test or the root test that we use here. Those are super useful for these, and so you're really just going to pick between those 2 for this first step in finding an interval of convergence. Now, because there is a square root of n on this one, that tells me I don't really want to do root test. I'm going to go with ratio test here instead. So remember, the ratio test is a limit as n approaches infinity of the ratio, so dividing 2 successive terms. So I have the n plus 1 term up top divided by the nth term here. And we are going to have the absolute value on these in order to get an interval. Otherwise, I'll just get one of the endpoints and I won't get the entire interval if I don't have an absolute value on there. And we'll see why that is as we go through this problem. Okay, so I'm going to start simplifying this. I'm dividing two fractions, so I'm going to flip the bottom fraction and then multiply the two. So it simplifies to this here. And the absolute value got rid of these negative ones. Okay, they just turned everything positive, so I don't need that. I still have an absolute value on the x's though, because x could be a positive or negative number. I don't know. So it doesn't ever completely go away on here because I'll always have an x there. Okay, so I can clean this up a little bit. X to the n plus 1 is the same thing as x to the n times x. And so I can cancel out the x to the n's, and I'll end up with just an x left over there. And then I went ahead and put those roots together. So that's just a little easier to evaluate that limit. Now you can take this absolute value of x and even pull it all the way out in front of the limit if it makes it easier for you to evaluate this. This is a limit as n approaches infinity, so this x here, which has no n's on it, can be ignored until I get to the final result. As far as evaluating the actual limit, I'm just going to focus on the part with an n in it. So this I can simplify by just dropping out the plus 1. We're going to infinity. A plus 1 has very little impact here. So really this is just going to simplify to sort of n over n, which is just going to be 1. So I end up with the absolute value of x for my result from this limit. And this is where I have to go back and remind myself, okay, I'm doing a ratio test. And according to the ratio test, when I take this limit, it will only converge when the result of the limit is less than 1. Okay, the series converges when the limit is less than 1, which tells me that my result, the absolute value of x, has to be less than 1 for the series to converge. From this, I'm going to get my interval of convergence. And now I have to go back to my pre-calculus days and remember how to solve an absolute value inequality. This is why we learned how to do that in our pre-calculus class. So luckily it's always going to be less than 1, so I don't have to remember all the scenarios of how to solve inequalities with absolute values in them. For the one where it's a less than, I just take the value on the right, and I can take the negative of it and throw it on the other side and turn this into a compound inequality. And that will allow me to get rid of the absolute value. Okay, if you think about it logically, the absolute value of x, if it has to be less than 1, then the x value has to be somewhere between -1 and 1 before taking the absolute value. And so I found my interval. Right? Sometimes you'll have like a number adding to the x or multiplying by the x. You'll want to get rid of that by solving it in all 3 spots. So let's say there was a +2 in here with the x, then I would subtract 2 in all 3 spots to solve this inequality further. But I already have the x alone in the middle, so I'm done with this one. And my interval of convergence is -1 to 1. The radius of convergence is going to be half the length of that interval. So if you can eyeball it, great. If not, you can always add the endpoints together and then subtract the endpoints and divide by 2. And that will give you half of the length of the interval. So here, our interval of convergence is 1. Now, we're not done yet, though, because I don't know at this point whether the series converges at -1 and 1. So maybe those points should be included in my interval of convergence. Maybe they shouldn't. I'm going to have to figure out which case I'm in. And it could be that one is included and the other is not. So I have to test both of these separately. So to test those, I remember these are x values. So I'm going to go back to the original series and plug them in for x. So starting with the left endpoint, when x equals -1, I'm going back to the original series up here, and I'm going to replace the x with -1, and then simplify it. So if I plug that in, I end up with a +1 to the n up here if I combine these two. And so that ends up just being 1 over the square root of n, or 1 over n to the 1/2. Now at this point, I have to go back to all of my convergence tests and find one to help me determine whether this series converges or not. Usually I focus in on the short ones, like p-series, geometric series, and divergence test are great quick ones that I usually try first before I go on to any longer tests. Sometimes the alternating series test helps out here as well. For this one, I see that I have the index is the base, and I'm in the denominator, and the exponent is the constant, so this is a p-series. And it's divergent because p is 1/2, which is less than 1, which tells me this is a divergent series. So that means that -1 is not part of my interval of convergence because it diverges at that point. Okay, so 1 down. Now let's do the same thing for x equals 1. Again, I'm going to plug it in for x and simplify. This time I end up with -1 to the n over the square root of n. Not a p-series because of that alternating piece on the top. So instead, I'm going to try an alternating series test. So for that, I have to show that the limit of 1 over the square root of n equals 0. You get to remember you leave off the alternating piece for this alternating series test. And yes, I have a constant over something that's getting infinitely large, so that will approach 0. And I also have to prove that the series is decreasing, or the terms of the series are decreasing. So ratio of successive terms work great for that. So the n plus 1th term over the nth term, I simplify that, and yes, this is going to be a proper fraction. This will be less than 1, so it is decreasing as well, which means that this one converges by the alternating series test at x equals 1. Okay? And all of the things I'm showing on the screen right now are all necessary part of explaining the solution. So don't leave any of these steps out. Make sure identifying the series tests you're using along the way and the qualifications for that test that the series meets. Okay, so I figured out -1 is not part of the interval, 1 is. So I can write this in interval notation using parentheses to exclude the -1 and a bracket to include the +1. And so just our final statement, there's our interval of convergence and the radius of convergence that we found. Okay, big breath. That was the longest ones. We're going to do some short ones too, so you can see the other examples, and so those don't trip you up when you run into them. So here's another example. I see a factorial in there. Definitely ratio test when I see a factorial. That's usually my go-to. Occasionally others will work, but not often. So I'm going to set up that ratio test just like before. So the n plus 1th term over the nth term. And I'm going to be able to cancel out the x minus 10 to the nth, and I'll be left with an x minus 10 to the 1st power. And I'm also going to simplify those factorials. Remember, I can rewrite the larger factorial, n plus 1 factorial, as n plus 1 times n factorial. I'm just pulling out the first term of that product. And then I can cancel the n factorials. So I'll end up with just n plus 1 times the absolute value of x minus 10. Remember that x has to have an absolute value still on it, because this binomial here could still be negative depending on the x value. Okay, so the absolute value here has no n's on it, so I'm going to focus on the n plus 1 to evaluate this limit. So n plus 1 as n approaches infinity, that's going to go to infinity. And it doesn't matter what x value I plug in, that will happen all the time. Except, of course, when x equals 10, because that would cause this term to zero out. So this limit is infinity everywhere for every x value except at its center at x equals 10. And well, according to the ratio test, when I get infinity, the series diverges. So that means that this series is going to diverge everywhere except x equals 10. So this is that first case where it diverges almost everywhere. My interval of convergence is just a point, x equals 10. And the radius of convergence then is 0, since my interval is just a single point. So that's one of the shorter ones. I don't have to test endpoints or anything like that when I get diverges for the limit. Okay, one last example. I know this is a longer video. I'm going to, again, do ratio test because of the n factorial there. So I set it up, ratio of successive terms. Don't forget the absolute value there. And then simplify this by flipping the bottom fraction and multiplying the two. The negative ones go away with the absolute value. And then I can do some simplifying here. So just like before, the factorials are going to simplify. I'm going to end up with an n plus 1 in the bottom. And the powers of x, I can split up this x to the 2n plus 2. And so just the x squared here will be left, and the x to the 2n's will cancel. So I end up with this. And I even get to drop off the absolute value because x squared will always be positive. And now I have a constant, an x value here, and the bottom is getting infinitely large. So this is going to approach 0 no matter what x value I plug in on top. So that means that this one converges everywhere. When I get a value that's always less than when I get an actual value with no x in there, so it really just happens when I get 0. Then that means that the series converges for all x values. So I get the other extreme, where my interval of convergence is negative infinity to infinity, and the radius of convergence is infinity. So the other short case. Okay, so we've seen each of the three possibilities to help you get through these problems. And now here's some guided practice for you to try on your own.